Now we got news that we can communicate with the astronauts. Now let's give a warm welcome and applaud to the astronauts.
Is established between ground and space. Our astronauts. In the middle is the lecturer of today's lesson, Wang Yaping, and she is China's second female astronaut.
Good morning, dear students. I am Wang Yaping, and I will give the lecture today. Good morning. I am Nie Haisheng, and I'm the commander of the mission. Good morning. I'm Zhang Xiaoguang, and I will be the photographer of this lecture. Now we are 300 kilometers above the surface, and I'm in the Tiangong module, and I must say hello to you. You know that witnessness is unique to the aerospace. So let's invite our commander to perform some difficult motions for you. No problem. So I can sit cross-legged in the air.
The commander of the Shenzhou 10 mission, Nie Haisheng, is going to do some little tricks in space in this weightless environment. He looks pretty much like a floating monk, bumping against a wall. So back in ground, during their training, engineers have simulated the space environment many times.
And in a witness environment, we are very skillful martial artists. So in a witness environment, does it mean that our body mass will turn zero? If we can measure that, that would be good. So I have a question for the students. How can we measure the mass of an object in our daily life?
So we're seeing a bit of interaction from the Tiangong 1 module in space and our classroom on the ground. Now is the Q&A period.
To measure the mass, and in the science lab, I can use a tray scale.
还有谁想？好，你把话筒递给旁边那位同学吧。
在家时，我用电子秤来测量自己的体重。
measure my own body mass.
如果要测大物体的时候，
If I need to
可以
measure
用曹冲
the
称
mass
象
of a big
这种
object,
办法来测量物体的质量。
I can use some kind of lever scale.
好，接下来还有哪位同学来说一下？好，第3排这位女生。
我想我们还可以利用动量守恒，利用碰撞，
And we can also
让带
use the
测物与一
conservation
个
of
已知质量的
momentum
物体发生正碰，这
and
样的
to
话，
let
通过
the two
它们的
objects
出没
collide
速
with
度
each
计算
with each
出带
other
测物的质量。
to measure the mass.
动量守恒的办法。
These students have so many
还有
questions
没
for
有
the
同学有其他的
astronauts.
办法呢？
Their
最快
curiosity
举
about
手的那个
space
男同学。
is huge.
亚平老师您好，我想到3种方法测量
I
物
think
体
about
的
3 methods.
质量。首先呢，就是
The first
说在中药房中可以
is
用
in
等
the
子，也
pharmaceutical
就是
store.
杆秤来
We
测
can
量
use
药
a
品
level
的质量。
scale to
当我们
measure
去
the
买菜
mass of
买
the
水果的时
medicines.
候，我
And
们也
when we're
可
buying
以
vegetables,
使用这个托盘秤
we
来
can use
测量蔬
the
菜水果
tray
的质量。
scale.
第3种呢，就
And
是
the
当我们
third,
进入物理实验室
when we
进
are
行
in
物
the
理
science
实验的
lab,
时候，我们可以使用弹簧测
we
力
can
计
use
先
a
测出
spring
物
scale
体所受的重力，
to
再
measure
通
the
过物重
gravity.
来计算出物体的质
And
量。
then we can know the mass.
好，亚斌老师。
同学们回答的
You
都
came
非
up
常
with
好。
very good ideas.
那么这些在地面上
But
测质量的
do the
方法，
methods
在
that
太
work
空
on the
中
Earth
还好
are
用吗？
can still at work in the space?
同学们看，
You see,
这是2
these are
个
two
一样的
exactly the
弹
same
簧，
springs.
弹簧的底
At
端
the other
分别
end of
固定
the
了
spring are two objects with different masses. If we are now on the Earth, then the stretch would be different. But now, the springs are in the same position. They cannot indicate the difference in the mass. So in space, if an astronaut wants to know whether he's getting fatter or thinner, what can he do? You don't have to worry. We have an instrument to measure the mass, the weight measurement instrument. And this is an instrument, and it is a strand. You can put the astronaut here, and then the commander and I will perform the experiment. You can guess the weight of our commander. Now the experiment begins. We let the commander stand on the instrument. And then we pull the steel rope to a certain place. And the pulling force makes him fall back to the initial position, and then we can know the weight. Now we see the weight. It's 74 kilos. Do you have the right guess?
So that was the first set of experiments done by our teacher in space.
And what is the physical principle behind this instrument? It is the Newton's second law of motion. The force imposed on an object equals to the multiplication of its mass and acceleration. If we can measure the force and the acceleration, we can know the mass. So we have a spring cam structure. It can exert a constant force, namely the force that pulling the commander into the initial position. And we also have a grading speed measurement system to measure the acceleration. And according to the law, we can measure the weight. Isn't it amazing? And now I have another question for you. In space, except for such a contraption to measure weight, are there any other methods? Now you can see my operation, and I can give you some hint. And this is a spring I just showed you. I pull the two springs into the same position and then let it go. So the vibration frequency is different for two objects. This is the same as if we do this experiment on the Earth. So, according to this phenomenon, can we come up with some other method to measure the mass? And you can think about that. Now let's do another experiment. This is a strand, and the rope can tie this little ball to the strand, which is a single pendulum, as we commonly see on the Earth.
So now the question is, if you set up a pendulum aboard an orbiting space vehicle, would the period be less than, the same as, or greater than it would be in our lab on the ground?
哎，它并没有像在地面一样做往复摆动。
It does not swing as it did on the Earth.
提高一点。
So let's move it higher to here.
它还是没有做往复摆动。
It doesn't swing either.
这是为什么呢？
Why?
因为在太空中，
Because
小
in
球
space,
处于失重状态，没有了回复
it is a
所以
weightless
不能
environment.
像在地面一样
There is no
做往
force,
复摆
so
动。
it cannot swing as it
那
does
如
on the
果
Earth.
我们推小
And
球
if
一
we
下，
push
小
the
球
little ball,
又会如何运
what
动
will
呢？
happen?
同学们，你们看到了吗？
You see,
非常的神奇。
it's
现在
amazing.
小球竟然在做圆周运动。
It's now orbiting. It moves in circular motion.
好，我们换个方向，再来给大家。
Now
Well, this is
another
indeed quite
direction.
amazing. Let's turn our attention to, let's turn to our studio guest,
哎，
Mr. Wei.
它仍然在
How
做
would you explain
圆
this
周运动。
phenomenon?
I think this
这是因为在太
demonstration
空
and
中
the previous
小球
all
处于失
all
重状
demonstrate
态
the important
这时我们给
concept,
小球一个
its mass
很
and
小
the
的
force.
速度。
So
它
what
也
we
能
measure
绕
the
摆轴
mass of
做
material is
圆周运动。
constant, but the
但
force is
是
not.
在地
It
面
depends
上
on
却
the
需要足够
acceleration.
大的初
So
速
on
这样
ground
的
we have a
表现
constant acceleration, about 9.8 meter per square of seconds. So that's why we take this default number and can merge the mass. It's because we know this one is constant, but in space we don't have this constant anymore. We need to calculate this one. That's why we use acceleration
同学
to
们，
generate
你
this
们可以
So this is
对比一
based
下
on
地
the
面的大
Newton's
概运
second
动。
law of
它
motion,
Exactly, on ground, yes.
explaining the relationship between force and acceleration.
好，在开始我们的下一个演
And
示之前，
I
同学
wonder
们你们
how,
有什么问题
Yanqing,
吗？
do you learn physics back in school? Did the
好，
teacher
请
do the
第
same
三排
kind
的
of
这位同学。
experiments in class?
Sure. I just mentioned the teacher in ground is my
王老师
high
好，
school
我
physics
非常
teacher.
羡慕您能
So
在
we have
太
do
空
the
中漂浮
same
着为我们讲
experiments
课
in the。
那么我也
classroom
想问一
before.
下，在
But now,
漂浮的过程中，您能不能感知到
when we
上和
study
下的这种
physics,
方
there's
位
a
感？
concept called
谢谢。
controlled group, which means there are variables in an experiment, and we change a single
这是一个非
single
常有意
variable
思的问题。
while keeping the others the
这
same.
样吧，
And this
那
way
我
we
首
can
先来给
determine
大
which
家表演
variable
一个小技
which
巧。
variable
不过呢，
will
要请我们的
affect the
厅长帮一
experiment.
下忙，
And
先把我
but we never face this situation. The gravity of this variable changed. So I think everything has changed since the gravity is equals 0 here.
现在呢，
Now we've got
对我
another
来
question
说
from our
这件
student
事上
in the classroom on the ground.
请厅长
He was asking if the astronauts would have a sense of direction in
现
space.
在呢，对于我来说，
And
这边又是上，
the
这边又
assistant,
是下。
actually he is the commander of the Shenzhou 10 space mission, is turning our teacher around, upside down.
同学们，你们看到了吧？
And you see,
在太空中，
in
我们
space
自身的感觉，在方位上是无所谓上
we
和
do
下
not
的
have
区
a
别。
very keen
无论
sense of
我朝
direction.
向哪个方向，我们自
Whether
身
we
的
are
感觉
heading,
都是一样
We
的。
feel the same.
不过在天宫中，
But in the
为了
Tiangong
便于
module,
工作和
To
生活，
make our
我们
life
也
and work
人
more
为地
convenient,
定义了
we have
上和
defined
下，
what is
并
up and
且
what is
把
down.
朝向
And we
地球的
define
一
that
侧
the
作为是
direction
下方。
towards the earth is
听错了
down, and we lay
答案。
floor on that.
接下来呢，我
Now
要给
I
大
will show
家
you
展
a
示一个
toy.
我们小时候
We
都很
played
喜
it
欢玩
when
的
we are very
玩
young.
具。
So the teacher is
同学
now
们，你们知
showing
道
the
这是一个
students
什么吗？
a toy
我
that
相
kids
信你
play
们
when
都
they
知
were
道
little.
它是一个
It is
陀
A
螺。
spin.
a gyroscope.
我们知道高速旋转的陀
The
螺具有
gyroscope
很好
that
的
is spinning
定轴
fast
性。
have good
陀螺
stability.
的这一特性在天上、
And
地上
The
是
good
完全一样
stability
的。
applies both
因
in
此，
space
有很
and on
多
the
设
earth.
备都是用陀螺
So
组
many
合
of the
来定向
equipments can achieve good stability by using the gyroscopes. And in the Tango module, we have some instruments using this principle to measure the position of the space probes. And now, I will show you a phenomenon that is hardly seen on the Earth, but is easily achievable in a weightless environment. Now I put this in the air and exert a force on that. And what happened? It is now spinning forward, and the axis has changed a lot.
Well, let's now get some insight from our studio guest, Mr. Wei Yujie from the Chinese Academy of Sciences. So this kind of phenomenon is quite unusual on the ground. I mean, you don't see it on Earth unless you're in a simulated environment.
Right.
But in space, it's quite amazing.
That's correct. That's all because of the loss of gravity. On ground, that's a force pulling down to the Earth, and here we don't have this limitation. And also remember that the space station is also rotating at a very, very fast speed, about I think it's 28,000 kilometers per hour. So that makes another big difference.
Things are so different 300 kilometers above us. The way they move is very different.
Yeah, if you look carefully in the inside, you see lots of knobs. And that's how the astronauts control the motion. You see lots of knobs in the top and in the wall. It's because if the astronaut is moving, if they don't contact the other body, they cannot stop themselves.
So they're moving because of outside force.
They can only stop the motion by external force.
It looks like magic. It looks as if there's a wire linking these two things together. Newton had 3 basic laws of motion that changed our lives forever, and this one is based on which?
I think all 3 of those in play. Newton had 3 basic laws. And all the 3
So Newton's laws of motion were considered the best mechanics law until Albert Einstein's relative gravity came into being. Is that correct?
I think I would say most physicists still consider Newton's law to be the best, because that's how we start all science and engineering.
He was a pioneer in classic mechanics. And now it's time to play with food.
Down 3,000 Shi, because in the weightless motion, it is impossible to have a cascade. Now I will squeeze a little droplet. Look at these lovely, beautiful little droplets. Does it remind you the word translucent? I would like to make a few more and make a necklace for you. Okay. In order to avoid it from floating around, I will retrieve it in a very special way. I can just have some drink to clear my throat.
So this demonstration shows 2 important concepts. It's one is no gravity. The other one is surface tension in water.
So we're talking about interdisciplinary here.
Yes.
It's not just one aspect of physics, but they combine different rules together.
Yes.
First of all, I will open the bag containing the water. And then I will put the metal ring in it very slowly. And then very gently I will pull it out. Okay, everybody, this is where magic happens. I made a very beautiful water film.
Is this the same that would happen on the ground? I mean, back on Earth?
Sometimes we can do so. If the size is small enough, because I just mentioned about the surface tension. So when the two different materials in contact, they can reduce the surface energy, so they reduce the surface tension too. So you see the membrane of water membranes sticking to the original steel cycles. It's because of the interface between water and the steel. They apply tension to the membrane, and it's like a stretching issue.
And just a little reference here, elasticity is a physical property of materials which return to their original shape after they are deformed. And I remember back in school, teachers would ask us why we can make bubbles out of soap water, or why mosquitoes can stand on the surface of water.
That's all because of the surface tension coming into play.
Right.
Next, I will try to press a Chinese knot onto the water film and see if it can sustain this Chinese knot. Okay, we press the Chinese knot gently onto the film. There we go. Isn't it amazing?
Well, the water membrane seems undestroyable.
So this water film is quite solid.
Oh, I think our astronaut is better defined as a magician other than a teacher.
In space, because we're experiencing zero gravity, we have a lot of phenomenon that is rarely seen on the Earth. And more magic will come later. Do you want to witness that? Let's try some.
We're now about 25 minutes into this class, and I'm already fascinated. If you've just joined us, you're watching our live coverage from China's of China's first space class. China's second woman astronaut, Wang Yaping, is now performing some physical experiments. And back on Earth, 60 million teachers and students are watching it live across China. And earlier in this class, she performed experiments based on Newton's second law of motion. And now, as our teacher explained, is water tension.
So, if we put more water onto the film, what will happen? Now, I will slowly inject water onto the film. Now, the film is becoming thicker and thicker.
So, Mr. Wade, does this water membrane, does it burst at all in space?
If there is no external disturbance, they will remain in shape. That's mainly because you can see that if we add small droplets into the big one,
but yes, that's growing. Also an outside force.
Right. It's basically because if they form one big sphere, and if we compare the surface area, which is proportional to the energy, so they try to minimize the surface area. So if you break this into two parts, you generate extra surface area. So that's not comfortable to the system. So they try to bring together and stay in the lowest energy level.
So it's really amazing to see how a water membrane has become a crystal ball.
You can see there are some little bubbles in this water sphere. Do you know why? It is because just now when we are injecting the water, this water bag contains some air. So now we are trying to get these bubbles out.
There's no way that's going to happen on Earth.
That's true. So we usually see the bubbles flow out to the surface and then back.
There's the reflection of our teacher in that water membrane. Yanqing, are you amazed? Are you fascinated by this class?
Yes, really amazing. Mr. Wei, is this phenomenon called the cohesion of water?
It's mainly the surface tension.
Yeah.
It's quite difficult to remember all the terminology relating to physics. Now we have another big bubble inside. Oops. So yes, the bubbles can burst. And now the teacher is injecting another bubble inside.
You can see the resistance when the needle, they try to pull the needle out of the water. You can see the resistance and they will change the shape.
Right.
It's because of the adhesion between the needle surface and the water.
That's one tough crystal ball.
You see, the two bubbles did not become one, and they exist separately. So we can see there are different phenomena in different environments. And now we are getting these bubbles out.
The bubbles out of the big one. It's unbelievable. You can basically do anything to that fragile water ball. So last time in the Shenzhou 9 mission last year, China's first female astronaut, Liu Yang, she performed a set of biological experiments, and this time the physical one.
I think the target for this time is try to inspire our young generations for the interest in outer space explorations. You can understand we are facing all kinds of challenges, and we do need more engineers and science devoted their life into this field.
Now, Yanqing, are you considering a change of major?
I will consider that.
So really, this is a perfect combination of education and space exploration.
Yes.
You can see the red liquid is spreading out in this water ball.
So before the launching the mission, lots of scientists actually involved heavily in such objects. They try to design experiments which can be doable in space, and also they need to somehow validate existing theories or exploring new physics.
Now all of a sudden the water ball has turned red.
Okay, let's have a close-up of this red water ball and enjoy this beauty.
This is really pretty. It seems that the color is floating inside the water ball.
I love to play with bubble when I was young. I think if I would have a bubble like this, I would be happy for all the day.
You will be very interested in physics if it isn't first. So you said one of the teachers on the ground was your physics teacher back in school.
Yeah.
The lady or the gentleman?
The lady, the female.
The lady. Now where is that water ball?
Absorbing the water ball by paper.
So it's gone.
Yeah. Papers.
Alright, now I think she's turning to another experiment. So much for water.
For example, in a weightless environment, we can have more evenly distributed and bigger semiconducting crystal for the basic research of materials. And by comparing the differences between Earth and sky and space, we can optimize the procedures on the ground. For example, the cold atomic clock will be more stable in frequency, and it can also be used for the future high-precision satellite navigation positioning system. In a word, the space technology's development and application has been penetrated into our lives, and I believe in the future we can have more scientific research and utilize the space resources to benefit mankind. Do you have more questions? We will be very glad to communicate with you.
The Q&A period. The teacher has completed all the experiments, and the students on the ground are raising their questions.
Good morning. And I would like to know if this water is brought by you from the ground or recycled in the space. Can this water be recycled for the use?
Actually, water in space can be very expensive. NASA, for example, has this program to convert body fluid, for example, sweat and urine, even into drinking water.
All this drinking water in Tiangong, in Shenzhou, is brought from the Earth, and in space, recycling of resources is very important. It requires advanced technologies and very comprehensive design. Therefore, for this short-time trip,
social issue. How do we use energy and all these environmental resources wisely for young generations? You can see in a very limited space, we do need to consider all these consequences of waste.
We now have very advanced cargo ships transporting crews and supplies to the space stations. However, it's still very expensive, and space, I mean, outer space is huge, but the space inside the module is a luxury.
Okay, do you have more questions?
And now we're seeing a question period from students on the ground to teachers 300 kilometers above Earth. And we're watching this live broadcast, and that's made possible by a series of communication satellites. For example, the Tianlian relay communication satellites.
During these few days, we did not see any space garbage, but we all know that they do exist. Although the chances for them to collide with the module is very low, but they are very large in amount. So if the collision happens, the consequences will be grave. Therefore, before the launching, we had a pre-analysis for this space garbage, and we also made relative preventive measures to ensure our safety. Thank you.
And any other questions?
好，请这边这位男生，这个第6排的。
If you've just joined us, we're watching a live coverage of China's first lecture from space. And now students are raising their questions to the teacher astronaut.
这个问题还是请指令长来给你回答。
Now she's referring that question to the commander of the Shenzhou-10 mission, Nie Haisheng.
In space, the astronauts will suffer from weightlessness, noise, and a cramped space. Weightlessness may lead to the cardiovascular disorder, bone loss, and muscular atrophy. To reduce the negative impacts, we sometimes do physical exercises, use medicines, and adjust our body liquid. And we also brought with us some equipment like penguin suit and the spring exerciser and bicycle ergometers. And this small table is adjusted from a bicycle ergometer, and then later we can reorganize it and make it a bicycle that is suitable to be exercised in space.
Really, to become an astronaut requires intensive training and rigorous selection process. It's almost tougher than anything most of us would ever experience.
And do you enjoy any view different from what you can see on the Earth? Do the stars still twinkle? And do you see the UFOs? It's an interesting question.
这确实是一个很奇妙的问题。
Yes, indeed, an interesting question. Through the window, we can see the beautiful Earth and the sun, the moon, and the stars, but we haven't seen the UFO. As we are now in the outer space, without the atmosphere, we can see the stars are shining brightly, but they do not twinkle. And in the absence of the atmospheric dispersion, we do not see the blue sky, but the dark black sky. And also something very interesting. We can see 16 times of sunrises and sunsets because we orbit around the Earth every 90 minutes. Thank you.
Well, astronauts in space would have to follow Beijing time during their journeys. Otherwise, time or a day, the concept of a day in space can be very abstract. Because she just said that they usually experience 16 sunrises in the period of 24 hours. So following Beijing time is probably the best and easiest way for them to keep track of time.
And thank you for your blessing. And I also would like to say to you, I hope you can study hard and learn more knowledge to contribute to the Chinese dream. The deep universe is a place full of secrets, and exploration is a never-ending journey. Let's work hard to that end. The space dream always carries some weight, and the science dream will always come true. Goodbye, dear students.
All right, that's the end of China's first lecture from space. The class lasted about 45 minutes, and the female astronaut is the teacher of this class. She performed experiments based on Newton's laws of motion, water tension, and many interdisciplinary aspects. Now, the two physics teachers on the ground are taking over from the astronauts to tell the students what they're going to see on Earth. They're going to perform about the same experiments, but the results would be very different.
Lecture. Although we have limited lecture time, we still have more time to explore after class. And today, we enjoyed a very wonderful lecture. And I believe this lecture will inspire us to explore this great universe. After returning to the Earth, the astronauts will have more chances to communicate with you, and you can ask them questions later.